Principles of Operating Systems, Chapter 6. External storage is much cheaper than primary storage. So if we can put suspended programs on disk instead of RAM, we can fit more processes into a system of the same price. At least if we put the suspended programs until they're ready to resume execution. Systems like this have been developed to use disk space as an inexpensive extension of memory space. We call these systems virtual memory systems. They are effective primarily because of what's called the principle of locality. Virtual memory systems have been developed to identify sections of RAM unlikely to be referenced soon and to copy these systems to disk, letting those areas of RAM be used by other processes or sections of the same process that aren't currently in memory. These sections of memory that will be copied to disk might be programs that are paused, but they could also be subsections of larger programs that are not going to be referenced immediately, even though the program is executing. Large programs can be divided into sections, and while using commands and data in one section, other sections of the same program might not be likely to be used soon and can be swapped out. A virtual memory adds a whole new level of complexity to an operating system. It's the operating system that has to manage the virtual memory system. It has to identify the program or segments that are not going to be referenced so they can be swapped out. It has to keep track of where these segments are swapped out to, where they are stored on disk. It has to be able to retrieve a section when it's determined that a running process is going to reference something that is no longer in RAM. It has to keep track of where in RAM the return section is going to be stored so that the process that's referencing that location can find it. Disk access involves two steps. First, they have to move the arm so that the read-write head is under the correct track. Time that it takes to move the read-write head to the correct track is called seek time. Then, when the head is on the right track, the disk has to rotate to the place where the sector with the right data comes to the head, read-write head. That's called the rotational latency. Seek time is typically much longer than rotational latency. So data transfer to and from disk is much more efficient if sections of data that get referenced together get stored on the same track, or at the very least on tracks that require very little movement to very little seek time. This observation is the motivation for developing paging systems for memory access. Virtual memory systems are subject to thrashing. That is, the computer resources become saturated and there is a constant state of reading and writing to and from disk, to the exclusion of application level processing. In order to use virtual memory, you have to be able to support the efficient repositioning of programs and data for transfer between RAM and cache, and for transfers between primary and secondary storage. The system that's been developed for supporting this is called paging. The operating system has several different management responsibilities: process isolation, allocation and management, modular programming support, access and protection control, and long-term storage. Paging systems provide support for all of the above. Paging is a system in which processes are made up of a number of blocks of fixed size. The blocks are called pages. In a paging system, a program references a memory location, a word in memory, by means of a virtual address. A virtual address is a page number identifying where the block is in memory, and an offset where the location is in the page. The pages can be located in just about anywhere in primary storage. It gives us a system for dynamically mapping the virtual addresses in the program and the physical addresses in main memory. We need such an independent system to implement a virtual memory system. In a system that uses hard disks, the contents of a page are normally going to be stored in the same sector or possibly adjacent sectors if the pages are that big. Page sizes are basically dictated by the sector sizes of the hard disks. In a system that has virtual memory with paging, processes and data sets are going to be organized in files, each one using one or more pages on secondary storage. Some of these pages have copies in primary storage, some will not. The CPU, of course, deals directly with things in primary storage, not in secondary storage. When the CPU references something in primary storage, it identifies the location, the page, and its offset in the page. The memory management unit, MMU, maintains a table of pages and records of whether there are copies in RAM and where, if they are, where they are. When the processor references an address on a page, the memory management unit determines whether that page is in RAM. If it is, the MMU directs the reference to the appropriate address. If the page is not in RAM, the MMU pauses the CPU process and initiates the process of getting the reference page into RAM. In a virtual system where you have paging, a process starts executing, only the initial section is loaded into memory. Locality suggests the first few operations are just going to reference the locations in the initial page. At some point, eventually, it's going to reference location in some other page, and then the process pauses and the system locates space in RAM for that page. Then it loads the page with the new location, and the process can continue. If there are lots of processes, as is likely, then all the available memory is going to be allocated. And the new memory reference is going to be to a location that's not in RAM, and there's not going to be any unused RAM locations. So some page in RAM has to be swapped out to make space for the new page. Then the page with the now newly referenced address can be copied into RAM so that the process can reference something in memory. Of course, this system requires some way of selecting a page to swap out. And that means you have to have some kind of algorithm that predicts which pages are unlikely to be referenced in the immediate future. Now, there are a number of strategies available for choosing pages for swapping out. Some of them are first in, first out, second chance, and clock, least recently used, least frequently used, not recently used, not frequently used, aging, and pure random. First in, first out is a strategy that simply replaces pages as needed in the page that has been in RAM the longest. It's easy to implement, and it seems intuitive that a page that's been in RAM for a long time is less likely to be referenced immediately than others that came in more recently. Unfortunately, it doesn't work that way. Many systems, this algorithm has been seen to target popular functions used by lots of processes. So a commonly used function would tend to get referenced early and often. When it gets swapped out, these pages get referenced again soon and copied back into RAM almost immediately. So FIFO is a poor predictor of future inactivity. It is, though, one of the simplest strategies to implement. It's low overhead. It requires very little bookkeeping on part of the operating system. The idea is obvious that the operating system simply keeps track of all the pages in memory, keeps them in a queue with the most recent at the back of the queue and the oldest at the front of the queue. When a page needs to be replaced, the page at the front of the queue gets swapped out and its space gets used for the new page. It's cheap and intuitive, but in practical applications, it performs poorly. And so in its pure form, it doesn't get used much. It is used in a modified form by the widely distributed VAX VMS operating systems. One of the modifications in the VAX system is the partial second chance. The second chance is a modified form of first in, first out. It works better than pure first in, first out, and it works almost as efficiently. It doesn't add much cost in the implementation. What second chance does is it adds a referenced bit to each page in the queue but when a page gets referenced, any reference, the reference bit is set, marking it as had been referenced relatively recently. If it is not set, the first page oldest page gets swapped out. Otherwise, the reference bit gets cleared, the page gets moved to the back of the queue, making it into a new page, but unreferenced, and the next page in the queue gets checked. So, in effect, what we're doing is creating a circular queue of unreferenced. If all of the pages have the reference bit set, then the system will work its way all through all of the pages and eventually encounter that first page again, which had its reference bit cleared. So if all of the pages have reference bit cleared, second chance is just pure first in, first out. So every page gets a second chance. An old page that's been referenced is probably in use and should not be swapped out instead of a new page that has not been referenced. Clock is an even more efficient version of the second chance because with clock, we don't have to move the pages to the end of the list. It does work pretty much the same as second chance otherwise. The clock algorithm keeps the list of pages in a circular queue. The hand of the clock, or pointer or iterator, points to the last examined page frame in the list. When a page fault occurs, we need to swap in something and no empty frames exist, then the reference bit is inspected for the page that the hand points to. If the reference bit is clear, if it's 0, then the new page is put in place of the indicated page and the clock hand is iterated. Otherwise, reference bit is cleared, and then the clock hand is incremented, and the system works with the next entry in the list, in the queue. Basically, then, is second chance, but instead of moving the page to a new position, it just changes the number in the pointer. So it points to a new position in the list. The least recently used algorithm replaces the page that has gone the longest without a reference. This, according to the principle of locality, should give optimum performance. Unfortunately, it's problematic in that it's hard to implement efficiently. Tends to require more processing and more overhead than other techniques do. It works on the idea that pages that have been used heavily in the immediate past are likely to continue being used heavily in the next immediate future. It can provide near optimal performance, at least in theory, but as indicated, it's expensive to implement in practice. There are some modifications, implementation methods that try to reduce the cost but keep the performance. Its biggest weakness is that there are several common reference patterns that can break it down and produce bad performance. Least frequently used is an algorithm that can be implemented more efficiently than LRU, least recently used. But LFU has a tendency to target recently loaded pages that haven't had a chance to have been referenced very often. Not recently used is an algorithm designed to keep pages in memory if they have been recently used. If it has been recently referenced, it might get referenced again. It's done in the following technique. It has two bits, a referenced bit and a modified bit. When a location is referenced, that reference bit is set to 1. If the contents of the page is modified, then the modified bit will be set to 1. Usually, this is done by hardware. At fixed time intervals, the timer interrupt triggers and clears all the reference bits of all the pages, so that as processes execute and reference locations, the reference bits get set, and reference bit then indicates that the page has been used recently. There are 4 types of pages then. Pages that have been recently referenced and have been modified since the last time they were stored on disk. There are pages that have been recently referenced but not modified. Pages that are not recently referenced but have been modified, so they would have to be copied back to disk if they're to be replaced. And then there are ones that are neither referenced nor modified. Note that it is possible for a page to not have been referenced but have been modified, since it could have been referenced and modified, and then the timer cleared all of the reference bits. When a page needs to be copied into RAM so that someone can reference a location, the lowest ranking page gets copied out, gets replaced. Type 0 if there is one. Type 1 if there is not any type 0. Type 2 if there's neither 0 or 1, and type 3 otherwise. Now, if there are no type 0s, then type 1 is preferred in rather than type 2, even though it's somewhat slower to select type 1, because first the page would have to be copied back to disk before it gets replaced. The not frequently used algorithm requires a counter rather than just a bit. And every page has its own counter. The counter is initially set to 0, and at each clock interval, all pages that have been referenced within that interval have the counter incremented by 1. In effect, then, they are keeping track of how often pages have been used. That means then that the page with the lowest counter would be the least used, and that is the one that will get swapped out if necessary to swap out a page. Now, the problem with the not frequently used is that it keeps track of how often the page is referenced, not when it was referenced, so that pages can get heavily used in a pass of a compiler, and then on a second pass will not be needed, but they are going to be favored to stay in memory over the pages that have been referenced in the second pass, because the second pass haven't had enough opportunity to build up their numbers. So we end up in the end with relatively poor performance. There are other scenarios also where the not frequently used algorithm would result in poor performance. For example, on operating system boot up. everything referenced in the operating system boot up is likely to be unused later on. But during the boot process, it builds up its number of references fairly quickly. Aging is an algorithm modification of the NFU algorithm with modifications taking into account when references were made. Instead of just incrementing the counters of the pages when they're referenced, which gives equal emphasis to the page references at any time, with aging, the reference counter first gets shifted to the right, has the effect of dividing the binary number by 2, and then adding a bit of a reference bit to the left bit on the binary number. As an example, if we have a page that as the clock ticks, it has a bit referenced in the first tick, nothing referenced in the second or the third or the fourth, but in the fourth and in the fifth, but not in the sixth. In those 6 ticks, the number, the counter adjusts with 1, 0, 0, 0, 0, 0. Then the next tick, since nothing is referenced, it's divided by 2, but nothing is added on the left. In the next one, nothing with no reference, so the counter is divided by 2 again. Then there in the next tick, there is a reference to something on the page, and we divide by the counter by 2 and then put a 1 in the leftmost bit. The next tick, there's a reference, and so we divide 1001000 by 2, and we get 100100, and add a 1 in the leftmost bit. Then the next tick, no reference, so we just divide by 2, and we get 011001000. This way, more recent page references have more impact on the number in the counter, the size of the number in the counter, than do the earlier page references, which are getting divided by 2. So pages referenced more recently, even if they haven't been referenced particularly frequently, more recently have higher priority than the pages frequently referenced. So you take, when we need to swap out a page, we select the page that has the smallest counter, because that will have fewer and less recent page references. Not widely used, but simply choosing a random page to replace actually works almost as well as just about any of the others. And it does have a big advantage. It's easy to implement. It doesn't involve any overhead. You just choose a random page in memory, swap it out, and copy in your data. You don't have any overhead cost for tracking page references at all, just random selection. It generally works better than FIFO. For looping references is better than LRU, although as a general rule, LRU is a little bit better for most situations in practice. It has been used. The OS 390 uses an LRU approximation, but when that starts to degenerate, it drops back to random. The Intel i860 processor used random replacement algorithm. Page replacement algorithms were hot in research and debate during the 1960s and 70s. Pretty much that got finished by developing sophisticated LRU approximations and working set algorithms. Since then, though, some of the assumptions that the systems were built on were invalidated, became less applicable to the newer systems, newer hardware and software. And research started going on again on how to deal with page replacement algorithms in the newer systems. In particular, changes in hardware and software that modified the performance of page replacement algorithms included increased size of primary storage, major increases in the typical sizes of primary storage. With so much more RAM, the algorithms that had to do checking of memory frames, memory pages, started requiring more and more time and became less and less practical. In addition, locality of reference that almost all of the algorithms were based on became less and less appropriate. Object-oriented programming involved larger numbers of smaller functions, and trees and hash tables being used for data structures, and that didn't have predictable memory reference patterns. Requirements for page replacement algorithms have changed due to kernel architectures for the operating systems. In particular, most modern kernels have unified virtual memory and file system caches. That requires the page replacement algorithm select pages among the pages for both user program virtual spaces and cached files. The goal of a page replacement is to minimize waiting time, so it has to take into account memory requirements imposed by other kernel subsystems that allocate and deal with memory allocation.